to MathStat341. This is lecture 2. What I want to do now is I want to talk a little bit about some of the basics of probability that we're going to do, some combinatorics, factorials, choosings, binomial coefficients, and then use that to attack a very interesting problem. And one of the themes that's going to be surfacing again and again throughout the semester is to do things well and efficiently. Actually, if somebody could close the door over there, this way we're not going to hear as much of the noises coming in and out. Thank you. So, just because you can do something does not mean you can do it in a reasonable amount of time. The first time I taught probability at Brown, I was coming from Ohio State. I got a copy of the book we were going to use, but I got a much earlier edition than was currently out. And at one point we calculated a binomial coefficient, and the book says, you might think you've solved the problem. I go, yes. And then the book continued, but you have to compute the binomial coefficient. What? Oh, this book is so old and the factorials are so large that it's non-trivial to actually evaluate the binomial coefficient at this point and actually finish the problem. So as computers get better, you can do more and more. But one of the things you really want to learn is, can you make good estimates? If you can make a fast estimate and be within a small amount, that's extremely valuable. Do you have some intuition for what the problem is? So I will start off with factorials. So n factorial is n times n minus 1 all the way down to 1. Is there anybody who has not seen factorials? Okay. So it has an interpretation. I'm going to go fast because hopefully everyone has seen this. It's the number of ways to order n objects when order matters. So president is different than vice president, is different than treasurer, is different than secretary. A U.S. vice president once famously quipped when asked, what is your job? By a foreign dignitary, he said, you die, I fly. My job is to express the condolences of the United States of America on your loss. There is a difference. In student council, or the House of Representatives, all the representatives are equal. And so that would be a situation where order does not matter. Now, there are some numbers that we want to know. What is 0 factorial? How many ways are there to arrange no objects? There's one way to arrange no objects. This is a definition. It turns out to be a good definition. Now, we'll get to some other interesting numbers later. I will just mention one right now. Anybody know what negative 1/2 factorial is? I'm sorry? You are close. You're off by a square root. If you square it, you get pi. So the number of ways to order negative 1/2 of a person is the square root of pi. How many of you have taken a statistics class with the normal distribution? You've seen this. They've hidden it from you. We will pull back the curtain. This is like Wizard of Oz. You'll see what's going on behind. You will see that negative 1/2 factorial is the square root of pi. N choose k. This is the number of ways to choose k objects from n when order matters. It's n factorial over k factorial n minus k factorial. And there's a good way to view this. View this as n factorial divided by n minus k factorial divided by k factorial. And the reason is the top is going to be n times n minus 1 times n minus 2 all the way down to n minus k plus 1. It's going to be, if I choose k people from n when order matters, let's say we want to do let's do 8 choose 3. I have 8 choices for the first person, 7 for the second, and then 6 for the third. That's the number of ways to choose 3 people when order matters. Well, now that I have 3 people with order matters, I can shuffle through all the different permutations, and they're all going to be equivalent. So if I have 3 people, how many ways can I order them? 3 factorial. And so I would then divide by 3 factorial. There are 2 things you need to learn how to do in mathematics. You need to learn how to do nothing by multiplying by 1, and you need to learn how to do nothing by adding 0. One of my math professors, Peter Jones, once remarked, now the log of 1 is 0, so they're really the same. So this is a problem where we want to either multiply by 1 or add 0. Any thoughts as to what we should multiply by?
Yes, 5 factorial.
5 factorial. So you want to learn to listen to the algebra. And so I'm working on a paper on a chess problem with a beautiful answer with a student from last year's probability class. And I want you to get to the point where you can see what to do. We know factorial. Factorial is a nice function. I have 8 times 7 times 6. It's screaming at you, please complete me. You know, I would love to be a factorial. Fine, we'll make you a factorial. Are we allowed to just multiply the top? No. Whatever you do to one side, you must do to the other. So we do this. And this is where you get the n factorial of a k factorial, n minus k factorial. This part over here is the n factorial divided by n minus k factorial. And this 3 factorial is just the number of ways of now reordering them. So this is a good way to look at the basics of the binomial coefficients. Right? Any thoughts on what -1 factorial should be? How many ways are there to arrange -1 objects? Given that -1/2 factorial is the square root of pi, you should be terrified at guessing. Right? Can somebody tell me what 5 choose 3 is?
5 factorial over 3 factorial times 2 factorial.
And what does that equal?
10.
That equals 10. Can somebody tell me what 3 choose 5 is? How many ways can you choose 5 objects from 3?
0.
Yes, if there's anybody who could actually do this, I'd love to see you do it after class. Right. Do we all agree that this is 0? Well, let's expand this. This is 3 factorial divided by 5 factorial -2 factorial, and it has to be 0. So this tells us that the proper way to extend the factorial to negative integers, what should -2 factorial be? I have no idea why the camera is going that way. Come back, come back. There you go. How should we extend the factorial to negative integers? I want this to equal 0. What should I choose for -2 factorial? Yeah, infinity. So -2 factorial should equal infinity. You know, there is a way to extend the factorial function. We'll talk about that later in the semester. It will be defined for all real numbers. In fact, it will be defined for complex numbers. And at the negative integers and at 0, it will expel. Other negative integers, it will explode. But if you look at this, it gives you a sense that that would be a good extension of the factorial. -1/2 factorial, that's a little bit harder to interpret. But at least this, I can kind of see what's going on. Okay. Anybody familiar with Malcolm Gladwell? Okay. Phenomenal person. He has a wonderful TED lecture on spaghetti sauce. I strongly urge you to listen to it. The probability book has an excerpt of his from sports. Anybody play sports here? Okay, what sport?
Football.
Okay, let me know when you have games. Your coach is actually no, this is being recorded, so I'll say I like the coach, I like this game. But any other sports here? Okay, what sport?
Cross country.
Cross country, okay. I haven't heard anything about cross country. Hockey is the one that is in the book, where what Malcolm Gladwell did is he took like the junior hockey championship in Canada and he replaced the names of the players with their birthdays. March 7 passes to January 3, January 3 passes back to February 4, February 4. It's all birthdays in like the first 3 or 4 months of the year. And the reason is, unfortunately, the way a lot of leagues work, if you just miss the age cutoff, you then stay in the lower league. But when you're young, typically the older you are, the bigger you are. Percentage-wise, it doesn't matter that much when you're as old as I am. Those few months mean nothing. But when you're very little, it makes a tremendous advantage. And so in a lot of these leagues, the best players then get more special treatment, they get more playing time, they get sent on to advanced training, and it actually propagates all the way up to the professionals, that the distribution of birthdays is not random. That there is a tendency for certain fields to have people born at certain times. This is not a biology class, I'm going to leave it as that for the general stuff. There are other situations where if you have people in a room, the birthdays may not be randomly distributed. Can anybody give me another situation where you may not have random distribution?
If you had like twins.
If you have twins, my wife is an identical twin. I lived with an identical twin in college. You know, the famous birthday problem is how many people do you need to have in a room before you have a 50-50 chance of at least 2 people sharing a birthday? This is a small enough class that I'm not confident of running. I mean, we can run it. This would be probably the first time it would ever fail in my life. I'm happy to do this. We'll do it after class when this is not being recorded, so people's birthdays are not public. But I am damn confident that at least 2 of us were born in the same month. I'm counting 12. Okay? It is possible that we do not have 2 people born in the same month. Okay? I'm willing to take the chance. Okay? Years ago, I actually convinced admissions to allow me at a prospective window on Williams to give free admission to everyone at my table if there weren't 2 people present who shared a birthday. And the students were excited. They started going around asking people for their birthday. Now, there were over 100 people at the event. I was not worried, as you will see from the calculation. I actually had to promise that I would pay some of the tuition, so it was going to be jointly financed by Williams and myself. For those of you who'd like to have happy marriages, you should probably share that information with your spouse beforehand. But the probability was so high of an alignment that I really wasn't worried. So let's calculate the probability that 2 people share a birthday as a function of the number of people in the room. We will assume that birthdays are randomly, uniformly distributed. Every day is equally likely. We're not going to worry about twins, about people on hockey teams or something like that. We're going to do the simple case. Then you can make it a little bit more interesting. I love this problem for a variety of reasons. The first is that you have to ask the right question. And it takes a while to figure out what is the right question. What do we need to assume? Well, we need to assume that there are no twins. Okay? One possibility is, if there are twins, you shoot one of them. Okay, there's probably issues with that, so we'll just assume that there are no twins, and if there's a pair of twins, we count them as one person. What else do we have to be careful about?
Each birthday of a person at the event has to be independent from others.
Right. But there's one thing we have to be careful about.
February 29th.
February 29th. So this should not be anybody here who was born on February 29th, correct? I have talked with admissions that I do not want anybody born on February 29th to ever take my probability class. It just screws up this lecture. It is not a protected category. You can discriminate on people based on whether or not they were born on February 29th. It's one of the few things left. Being a Yankees fan, that's also acceptable. But why would February 29th be so bad? Yeah, the probability of having a birthday on February 29th would be a little bit less than the probabilities on other dates. And so it's much easier to assume that we don't have anybody born on February 29th. So again, this is why I love the problems. There's these small little subtleties you have to be careful about. Now, one way to solve the problem is constructive, is to look at all the ways we could have at least 2 people share a birthday. So one possibility is there's exactly one pair of 2 people, or there's exactly 2 pairs, or exactly 3 pairs, or there's a triple and a double, or a quadruple and a triple. And when you start looking at this, oh my lord, there's so many possibilities, to enumerate all those possibilities would be painful. There's a better way to attack the problem. Rather than enumerating all the ways it could happen, what could you do?
Start with extreme cases.
Nope. Not bad, but
Like, find the ways it could happen.
find the ways it couldn't happen. And then the ways it can happen is just 1 minus the ways it can't happen. So a lot of times, it's much easier to find the probability of a complementary event. So 2 events are complementary if their probabilities sum to 1. If I can figure out the probability that something doesn't happen, I can pretty much figure out the probability that something does happen. Any Seinfeld fans here? Okay, so I will just talk to you. Do you know the episode The Opposite?
I saw all the seasons a while
Okay, so George Costanza, the most generous description of him is he's a loser. And there's one episode where he's remarking that every decision he's made in life is wrong. And so his friends convince him that if every decision you make is wrong, then if you do the opposite, it will be right. And he starts doing the opposite. And I will send the clips later, and he's doing things that you would not believe you could do. He's being interviewed by the New York Yankees. Steinbrenner, who is actually a Williams alum, goes up to him and he sees him being interviewed. "It's a pleasure to meet you." And George responds, "I wish I could say the same to you, but," and then launches into a tirade. Now, if there are only two options, calculating one gives you the other. Doing the opposite gives you the right. Sadly, most of the time in life, there's more than two possibilities. So you need to be extremely careful if you're using complementary probabilities that you really have two mutually disjoint items, and the two things together is everything. So if we want to know the probability that two people share a birthday, we can just calculate the probability that no two people share a birthday. So P of n is the probability no two in n share a birthday. And we want to calculate the probability. So if you have one person in the room, what is the probability that no one shares a birthday? 1. Okay? Answer is absolutely right, but I'd like to write 1 in a different way. How else could I write 1?
365 over 365.
So that's one way, is I could write it as 365 over 365. And there's an even better way to write it than 365 over 365.
1 over 1.
Almost.
2 over 2.
No. Any thoughts?
1
1,
minus
0. So that's the probability, if you have one person in the room, that everybody has a distinct birthday. Now a second person walks in. What's the probability the second person doesn't share the first person's birthday? So this is 365 over 365. When the next person comes in, what's the probability they have a different birthday?
364.
And I can write that as 1 minus 1 over 365. And I can keep going down to 1 minus n minus 1 over 365. It's annoying if I'm doing n people, I stop at n minus 1 because I'm counting from 0. I might have told you my son learned when he was very young that daddy's a mathematician. If daddy says you can do things 3 more times, if I start counting at 0, daddy will smile and I can do it 4 times. You have to be careful with stuff like this to make sure you stop at the right place. We don't go down to n, we go down to n minus 1. If you have a calculator, you can just keep multiplying these until you get to a half, or approximately half. But if I change 365, imagine we move to Pluto. And then there's over 90,000 days in a year. How many people do you think you would need on Pluto? So sometimes when I teach this class, I do it with clickers and I ask you, roughly how many people do you think? So if I had 400 people, would you be confident? Yes, pigeonhole principle. There's only 365 days with 400 people. Clearly, you've got to have people overlapping. What if we only had 180 people? Would you be pretty confident? Yeah, because once you're already at 170, for the next person to come in, they have almost a 50-50 chance of matching birthday. And so just getting a few more people like that, you should be really good. So I would be shocked if we had to be anywhere near half of 365. But what's the correct answer? Is it the square root of 365? Is it the fourth root? Is it the log of 365? How does it change as we replace 365 with, say, d days in a year? Now, we can write this in many ways. One way of writing it is 365 factorial divided by 365 minus n factorial 365 to the n. So that's just writing everything out, the product we had down below. If you try to put this in your calculator will no longer talk to you, right? 365 factorial, it'll overflow. Unless you have a really good calculator. But most of the calculators crap out between maybe 60 and 80, 85. And this is what I meant from the comment from the book, that now you have to evaluate things. This is not necessarily easy to evaluate. Okay. I'm not quite sure why it keeps turning like that, but okay. So now, how would we evaluate this? Well, there's a nice way to write this. In calculus, you've hopefully seen summation notation. We also have product notation. So Pn is the product, k goes from 0 to n minus 1, of 1 minus k over 365. And if you want, we can do 365 and then do a search and replace 365 with d later, or I can put in d right now. What do people prefer?
Put in D right now.
Put in d right now. So first loud voice often wins. Doesn't really matter. So if we have d days in a year, this is the probability that if we have exactly 10 people, that we do not have 2 people sharing a birthday. And we want this to equal a half. So we want to solve for n such that this equals a half. When you take a class from me, one of the things that you must leave with is a Pavlovian response whenever you see a product. So who knows who Pavlov was?
He was a psychologist who trained dogs and animals to have a certain reaction.
Yes.
For example, he trained a dog to salivate when the sound of a bell.
Perfect. So he trained animals to have certain responses to certain stimuli. Right? I want you to have a certain response whenever you see a product. What should that response be? Any thoughts?
Happiness.
I like that. I like the idea of happiness. No. What response should you have whenever you see a product? Yes.
Make it a sum.
Yeah. How do you summify a product? What do you do to turn a product into a sum?
You keep the log.
You take logarithms. So I got these from family members who used to be engineers. Slide rules. Before computers, these were valuable. And then my favorite is the circular slide rule, much, much better. Whenever you want to do multiplication, you can turn multiplication into addition. Addition is easy. We have familiarity, we have experience with addition. We don't have the same with multiplication. So the idea is, if I give you something like this, I should convert it to a sum. You've taken classes in calculus where you've dealt with sums. You have not dealt with products. Now, to some extent, it doesn't really matter. I can go back and forth between the two of them using logarithms. But if you're familiar with one thing, it's nice to use that. How many people have done a Sudoku? Would it matter if instead of using the numbers 1 through 9, I used vegetables? But it would probably take you a little bit more time to process things. So we have a lot of familiarity with sums. Let's convert this to a sum. So the log of Pn is going to be the sum, k goes from 0 to n, of the log of 1 minus k over d. And now we recall the log of 1 minus x is equal to negative x minus x squared over 2 minus x cubed over 3 minus x to the 4th over 4, dot, 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 dot. If x is small, the only term that matters is the first. So what I'm doing now is I'm trying to approximate a complicated expression with a simple one. If I wanted to have upper and lower bounds, I could do an upper and a lower approximation for the logarithm and deal with that. And what's nice is that there'll be separate terms. So I'll leave that as an exercise to you as to how would you approximate things. So now what I can do is I can take this and I would get the log of Pn is approximately the sum k goes from 0 to n of negative k over d. And again, you could keep more terms and have a slightly better answer. I think this is good enough. We know how to sum positive integers. Oh, I'm going to n minus 1. Now the first thing to note is the sum on the right is negative. Does it surprise you that this is negative? What is Pn supposed to be for us? What do we want Pn to be? We want it to be smaller than 1. We want Pn to be a half. Right? We're trying to find the n that gives us a probability of a half. Well, the log of 1/2 is going to be a negative number. The log of 1 is 0. Anything less than 1 is going to be negative. So the fact that we have a negative sign here is actually very good. So we can multiply by negative d, and we get negative d log Pn is approximately the sum, k goes from 0 to n minus 1 of k. Yes?
On the, over the sigma on the left should be an n minus 1, or is it?
This should also be an n minus 1, yes. Thank you. And I actually initially put an n over there by mistake and corrected that, but did not correct the other one. So we want to sum the first n minus 1 integers. Well, we have the following fact. 1 plus 2 plus m, if you call that Sm, if you add the numbers in reverse order, you also get Sm. And now when you add, well, this is just twice Sm. 1 plus m is m plus 1. 2 plus m minus 1 is m plus 1. All the way to m plus 1 is m plus 1. So we get m plus 1 a total of m times. So this is Gauss's trick. You might have seen a proof of this by induction. This is a way to prove it without induction. We get Sm is m plus 1 over 2. If there's time later today, I'll talk about ways to estimate the value of this sum. But we have an explicit formula for this. You could also approximate this by an integral and say that this is approximately integrating x from 0 to n minus 1. There's lots of things you can do, but we can actually evaluate it exactly. And so now I can say, this over here, let me just keep moving down. So we get negative d log Pn is approximately n minus 1 times n over 2. And we want Pn to be a half. So we get d log 2 is approximately equal to n minus 1 over 2. How would we solve this? We have to solve for n. How would we solve?
Divided by d.
Well, we're trying to solve for n. What kind of equation is this?
Quadratic.
It's quadratic. How do we solve a quadratic equation?
Quadratic formula.
Quadratic formula, right? It may not be pleasant. It's much better if I can just stare at it and factor it. But we have a recipe that will always solve something like this. We can solve for this. Do you want to use the quadratic formula? It's going to be a little bit messy. Let's do another approximation. N times n minus 1. Approximately, what is n times n minus 1?
N squared.
It's approximately n squared. You can do a little bit better though than n squared. Well, n squared minus n is exact. So what I'm going to do is I'm going to say d log 2 is approximately n minus a half squared over 2. So your answer was good, but you were biasing the n. You're giving a little bit more weight to the larger one. Let's split the difference. What's nice about this is if you square this, you'll get n squared minus n plus a quarter. So you're not missing by much. And it's going to make the math a lot easier. And so now when you solve, you'll get, after the dust settles, n is approximately 2d log 2 plus a half, or n is approximately d.
I'm confused why it went to 2 from
Wait a minute.
1 over 2 for Pn.
I'm sorry?
On the second line, it's like Pn equals 1 over 2. Should it be log 2 for 1 over 2?
Over here?
Yeah.
Okay, I just realized there's a mistake over here. Because Pn is 1/2. So the log of 1/2 is negative log 2. So the negative reinforces the negative sign there. But I made a mistake, is it should be the square root of this. Right? I first multiply by 2, then I take the square root, then I add a half. And so when the dust settles, you get n is approximately this, I'll write it as d, the square root of d, and then the square root of the log of 4 plus 1/2. It turns out this is a really accurate approximation. And what's wonderful about this is you can see how the critical threshold varies with n. And so the book has plots of what this looks like. I urge you to just code this in something and just see yourself. You can even do Microsoft Excel, for Earth. It's not too bad. You need n to be around 22 to have a good chance, have a 50% chance. As n gets larger and larger and larger, operations research is around 40. I'd be very confident doing this in operations research. Here, with only 12 people, what could I do as a professor to increase my chance of winning if there are only 12 people? Yes?
If there's anyone within a day or within a week.
Right, so one thing is I could expand things and say it doesn't have to be the same day, it has to be within maybe 1 day or 2 days or within a week. The other thing is I could just have several different IDs on me. And then I go last. And then when somebody says January 3, oh, I'm January 3. And so if you have enough stuff like that, you can pull it off. I'll take out my ID later before we do this, just to be fair. Okay, so with 12 people, I'd be terrified to do this. The odds are not in my favor. But this shows you the power of setting up a problem and looking at it the right way. By looking at it as complementary probabilities, rather than looking at all the ways to have 2 people, 2 pairs of 2, 3 pairs of 2, a triple and a double, a quadruple and 2 single, it's a nightmare. We just look at the probability it doesn't happen, and so the probability it happens is 1 minus that. Then we had a very long product to evaluate. And the key idea is when you see a product, think logarithms. If you are voluntary at Williamstown Elementary and you're trying to teach 3rd graders how to multiply, okay, you can resist the temptation to take logarithms. Other than that, in a theoretical math class, when you're trying to manipulate expressions, logarithms are extremely powerful. Depending on how much accuracy we want, we just take more terms. And so over here, I'm throwing away something that's negative. Well, since everything is negative here, this will tell me my error is going to be in one direction. I could add some things back or subtract some things back and get upper and lower bounds and do a more careful analysis. There is a formula for sums of squares, and we can continue to do this without too much trouble. So I strongly urge you to learn how to program, and we'll have a class devoted to programming very simple problems. I am not expecting you to be able to write 5,000 lines of code to analyze something very complicated. I am expecting by the end of the semester, you can do things involving for statements, while loops, something like that. You want to be able to simulate, let's say I choose 35 people, uniformly birthdays from 1 to 365, and I want to see what's the probability that they share a birthday, that at least 2 people share a birthday. So you would just run the simulation, see, did I ever choose the same number twice? I want you to be able to write code like that. And there's a lot to learn about coding well. Fortunately, there are many times when you do not have to code well. You just have to code. So if you only need to run something once, and you don't need the answer too rapidly, you don't have to code well. If you're designing something for a cell phone, or to transmit information, if you want to stream video content online, yes, any efficiency you can gain is valuable because you're going to be doing it so many times, the savings will be tremendous. When I was a postdoc at the American Institute of Mathematics for a summer, somebody gave a really nice number theory problem. And so, can I erase this stuff now? So you take the digits 1 through 9. Each digit is used once and only once. And you want to create the following. So you have 1, 2, all the way up to 9. You want A over 10B plus C plus D over 10E plus F plus G over 10H plus I, and you want that to equal 1. And it turns out that there's a way to assign the numbers 1 through 9 such that this works. My colleagues was proving advanced theorems about the locations of certain digits. And, they were really looking at this problem at a high level. What do you think I did?
Computer program.
Yeah, computer program. So how many ways are there to choose the orders of the A's through I's? How many ways can we put the numbers 1 through 9 into these slots? 9 factorial. There's a reason why I'm doing this problem today, right? Foreshadowing the art of a great lecture, right? 9 factorial. Well, 9 factorial is 9 times 8 times 7, 6 factorial. 6 factorial is famous. 6 factorial is probably like the last one people just know off the top of their heads. 6 factorial is 720. If you don't, 5 factorial is 120 multiplied by 6 is 720. So this is 9 times 8 times 7 times 720. Well, 9 times 8 times 7, that's less than 1,000. So there's at most 720,000 possibilities. And I know 8 times 7 is 56. So I was approximating this with 100, it's only around 56. So I might guess that maybe there's half of 720,000. So maybe around 330,000 possibilities, ballpark. It's nice to be able to look at things and get a rough sense of how bad is this computation. If I told you your homework this weekend is to look at 330,000 cases by hand, there would be either protests, burning an effigy, burning an actuality, something like that, right? Because this is not something you do by hand. But for a computer, 330,000? You're like, sure. What else do you want me to do for the rest of the second? It's trivial for a computer to do something like this. Now, you could actually do some advanced coding and say, well, the order of the 3 fractions doesn't matter, so I can reduce the 9 factorial. If you tried to do that, it would take you more time to code that than to just run the inefficient code. And so I want to just really drive home some of these lessons on programming. Computers are now so powerful that you don't have to worry about a lot of this stuff. When I was a kid, we had, I think, the extension for the Timex Sinclair 1000, I think we had 16 kilobytes of memory. And it was a real challenge. The Voyager space probes, I believe, have far less computing power than on your cell phone. When you're writing code now, you can afford to be inefficient because it's so fast. This doesn't mean I'm against people coding efficiently, but just be aware of what's needed for a problem. For the birthday problem, it would be great, that's a great thing to try. Can you write a code to simulate, say, 1,000,000 times 35 people coming in and seeing what the probability is? Or better yet, where you ask the user, how many people would you like? Maybe I want 12 people, and then simulate what the answer is. And then you can compare it to our theoretical prediction. All right, any questions on the birthday problem? Yes?
What was D again?
So D is just the number of days in the year. So if you want to think of D as 365. And it tells you that the answer depends on the square root of D. How many of you have heard of the Pentium bug? Okay, so for a while, Intel called their processors the 286, the 386, the 46. And then instead of having the 586, they came up and they said, it's called the Pentium. And the processor is the most important part of your computer. And you want an Intel processor. Well, Intel actually knew that there was a defect with their processor. If you had to do too many divisions in a row, it would actually make a small mistake. Now, most people don't need to do 1 billion consecutive divisions to 9 digits accuracy. It didn't really matter. But nicely, a mathematician was investigating the sum of the reciprocals of the twin primes. It turns out this converges. And when he was trying to get more digits on a Pentium, it wasn't matching earlier results. And this became a huge multi-million, I think $100 billion fiasco for Intel, where the other competitors said, we agree with Intel that the processor matters. Ours can divide. And so Intel had to offer you, we'll give you a replacement processor to anybody who needs one. And again, almost nobody needs to worry about this. You're not dealing with 1 billion divisions to 9 digits accuracy if you're looking at your Excel spreadsheets for like your family income or something like that, or grade sheets. But it was a huge fiasco for them. This is one of the advantages or benefits of pure mathematics, is it is a way to test. How can you trust the output the computer gets? There's a reason why I want to spend time today talking about this. We are becoming a very technological world. Do you trust the output? There's been a couple of cases now where they've detected that voting machines are not recording people's votes properly. Can you trust what you're being told? So I want you to have a healthy degree of skepticism. I'm going to give you a homework problem to look at some very interesting fractions. And for these fractions, you do have to be able to divide somewhat well. So I want you, I think it's on the homework 999, I think? No, 99899. Okay, 1 over 998,999 and 1 over 999,899. So look at those fractions. I think that's a homework problem. Do the division really well, and you should see something interesting. And then when you see something interesting, is it a coincidence, or is it perhaps a deep theory that Professor Miller is going to get to later in the semester that will explain why these are good fractions to look at? Last thing I want to just mention is, how many of you know the phrase QWERTY? QWERTY. Okay. What does QWERTY mean? Where does it come from?
You know that has to do with keyboard.
Yes.
I'm not sure.
So on the standard keyboard, it starts off QWERTY. Why would we do this?
So I think the original theory was to put the vowels on the middle row and frequently used keys. Or like, basically like have some type of layout to make it so that it's like convenient to type.
No.
No?
It's the opposite. It's to slow down typing. The QWERTY keyboard was designed to be inefficient. Because on the old typewriters, if you hit two keys that were close to each other on the keyboard in quick succession, they would go down and they would sometimes jam. So this was made to make you alternate left and right hands and slow you down. The Dvorak keyboard is the most efficient one now for English. Why do we still use the QWERTY keyboard? We don't love you. Your parents don't love you. Your teachers don't love you. We would have to change. We would have to learn something new. We're not going to do that. We're going to make you suffer like we suffered. And then what will you do? Teach the same thing. You had to go. When I taught at Princeton, we had multivariable calculus, and I remember asking the students one year, so did you like the problems where two cylinders intersect at right angles and you have to calculate the volume of the region of intersection? No! Okay, should we remove those problems for next year? Hell no, we have to do them. We want them to do them. And as a Yale man, this is when I smiled and said, should I tell you how many years in a row I've now had this conversation? That no class has stood up and said, enough. Things get institutionalized. I want you to really be thinking about why you're doing what you're doing. Okay? And so, for a lot of things, the reason is because this is how it's been done. That doesn't mean it can't be done better. And the last thing for today is Babylonian mathematics. So the Babylonians loved base 60. 60 is great when you don't have a decimal system, when you don't have calculators. If you want to divide things up into 2s, 3s, 4s, 5s, 6s, can't do 8s, can't do 7s, can't do 9s, but can do 10s, can do 12s, can do 15s. 16 splits up very nicely. But if you think about being a young Babylonian scholar, if we need to learn things, we only have to learn tens tables to multiply numbers. Because then you can do anything else by doing positional arithmetic. There's 100 things to learn. And then you realize, well, that's actually not 100 because x times y is y times x. So there's only 50 or 55 things actually to learn. So the actual answer is there's 10 choose two ways to choose two distinct numbers, plus 10 choose one way to choose the same number twice. So it's roughly a half of 100. So for the Babylonians, your table, oh Lord, 60 times 60, half of that, 1,800. So you write this down on clay tablets. You don't bother memorizing all of it. Well, clay tablets are heavy, they're expensive, you would have to make them for everybody who wants multiplications. What did the Babylonians do? If they wanted to multiply x and y, their brilliance was the following. They looked at x plus y squared minus x minus y squared, and they divided by 4. So rather than doing one multiplication, they do one addition, two subtractions, a division, and two squares. This is the notion of a lookup table. In old probability classes, you would actually have lookup tables for the bell curve, for the normal distribution, maybe for the exponential as well. We don't bother. You can go online and you can get them, or you can just go to various web pages and it will tell you what the probabilities are. We no longer need to really have these printed. But if you think about this, it's very special multiplication. It's squaring. You only need a table of squares. You need either maybe 60 or 120 squares. That's not so bad. And so the idea here is that you were able to do something more efficiently. In probability, when we were doing these calculations, at the end of the day, you want to be able to compute things. When we had the expression involving that product, how do we clean it up to something that's nice and closed form? How many of you, I know I've asked this before, how many of you are in the econ dark side? Nobody's even arguing the dark side. Excellent. It's unlikely that you will have something with a closed form answer where all the parameters are nice and you can change the parameters and you will see how the economy will change. You have to do it up in simulations and you have confidence bands. It's wonderful when you can have a closed form expression, but it's very hard to get to a closed form expression. And so I'm trying, as we go through the course, to give you some ideas of how to do the calculations to get there. All right, so I'm going to stop here.